We'll now switch to our next talk by Subhodeep. Subhodeep is an analytics professional who enjoys the craft of turning messy business problems into clear, data-backed answers using a mix of statistics and machine learning. What stands out is his learning mindset. He's actively building depth across domains, eager not just to study methods, but to apply them in real settings where the problem is ambiguous and the impact is measurable. And outside work, he's a serious Kaggle enthusiast with strong finishes across competitions. Please join me in welcoming Subhodeep.
Check. Hello, check. Cool. Thanks. First of all, thanks Anshul for the introduction. And I see a pretty good amount of audience here. And thanks again the Technology Tribe for giving me opportunity to present my work, which is why static ranking fails for personalization at scale in the Mosaic forum. So before I start, I just want to know how many of you guys are using BigBasket or any quick commerce apps. If you can raise your hands. Oh, okay. So there's a pretty good number of people who are using BigBasket. So you might be familiar with the phenomena that I'm going to show. So let us take the journey of one of our most valuable customer, who is Mehul. Mehul is a chocolate-loving user. He came into BigBasket app multiple times and bought chocolates multiple times. And before the chocolate day, to present his girlfriend, he has again come to the BigBasket app and wants to buy chocolates. Now, as soon as he landed up on the particular home page, what experience he sees? He sees something like this, where we have multiple widgets, like cool card finds. These widgets we call as assets. So, as the assets we can see, the first asset is on fruits, followed by glue. But is it what he is intended for? Or he should see an experience like this, where first he's seeing the chocolates, followed by maybe second preference, which is meat. So definitely there is a gap. In the first screenshot that you guys can see here, the ranking that we can see is mostly a availability based and an area based ranking of the products, which is more generic, and everybody who is logging into BigBasket app will see this. Whereas the second one is more of a personalized view, where what exactly Mehul likes, that is shown in the top. This problem we are facing in the last year, specifically in our search and our home pages, which is affecting our conversions. That is why we took a goal last year, specifically on Q3 of 2025, to come up with a more personalized framework which will replace this generic availability based framework, so that every customer, when they lands up in BigBasket, gets a personalized experience. So as I already mentioned, in the previous situation, the ranking was mostly generic, availability based, area based, and also it was uniform across different regions. So people of Bangalore will see the same experience like the people of Delhi, and it is mostly based on the assortment of the products. And we want to move from the availability based ranking to a more personalized based ranking, and we want to do it at scale. But in order to accomplish this, we have some kind of constraints which we want to encounter here. The first constraint is the low latency and the existing serving systems. So as you guys can see on the right side of the slide, for search we get more than 30 million searches per month with a latency of 120K requests per minute. On the other side, for the dynamic pages or the home page, we get more than 40 million impressions per month with a latency of 60K requests per minute. So with this new framework, we don't want to sacrifice on this existing latency. The second one is the storage, which is massive scale of data. As you can see, for two cities, which is Bangalore and Gurgaon, and these have the highest penetration of customers. So for them, we have more than 10 million users, We have around 10,000 brands and more than 2,000 categories. So this is huge in terms of SKU. It translates to more than 80,000 SKUs. And while building any framework, we have to work with this massive scale. And since all the users are not shopping on all the products, there is a lot of sparsity in the data. The third, BigBasket being a frugal company, as you guys all might know. So along with the business efficiency or the performance of the product, we are also want to create a cost optimized and cost efficient solution. For this, we wanted to avoid maximum use of EMR, which is usually EMR or Spark clusters, which is usually costly. And that is why we want to create a framework with which we can use minimal EMR or Spark. Finally, our search works at an SKU level, for which we need brand and category information both. And for dynamic pages, uses at a category level only. So we want to create the framework in a way so that we can cater to both of these use cases separately. Given that, how we have done the problem formulation? So we have broken it into 3 steps. The first step is that data and feature level consideration. The second step is machine learning model itself. And the third step is the final processing layer, which I want to discuss in more details in the upcoming slides. And different level of optimizations are done on each level to make the solution extremely worthy with a lower cost. So if there are any folks who are present in this forum who is coming from maybe any startup or any other company who wants to develop personalization models at scale with a lower cost, they can take our learning, which I'm going to present in the upcoming slides, and you can use these learning into your work to come up with a very cost efficient and high performing personalization engine. So first, as I mentioned, we will discuss about the data considerations. So since we have 2 use cases of search and dynamic pages, the first we have created 2 data marts. One at a brand level and the other one at a category of the product level. And for both of these data marts, we have considered last 1 year. The advantage, again, as I mentioned multiple times, that it is helping to cater the 2 requirements properly. And again, there are some products which a lot of you guys might find that which usually does not sold much due to the visibility, because we don't show it to the customers. To improve the visibility, we aggregated the data at a brand and category level so that we can bring up those products and show up to the customer who actually wants it. For these 2 data marts, we have used the following tables. So we have used brand and category level interactions and user and product metadata. For brand and category level interaction table, we have created for different user and different brand or category, we have created a weighted combination of the interaction scores. What is a weighted combination of the interaction scores? We have taken a weighted combination of the number of orders that they are making and the add to cart. So add to cart or the add to basket, you will see that whenever in an e-commerce you come and you shop and you see and you just add the product, plus sign that gets added and it adds into a cart. So we calculate the number irrespective of whether you buying it or not, that number will be there. So we have given a higher weight to the orders and a comparatively lower weight to the add to basket. For the user metadata, we have used recency, frequency, monetary, and the tenure matrices. For the item metadata, we have used price, views, clicks, and ATV. So the advantage of using these tables as well as the features are that this is helping us to find out user behavior and match it with the user intent interactions, and behavior is mapped through the metadata. The another important use case is we have cold start. So suppose if there is a new SKU or new product comes in which was not there earlier, we can make use of this metadata information, and using our recommendation engine algorithm, we have been able to map these products with a particular user who might have a natural need for it. Now, the main key takeaway is we have built this all these data marts on iceberg tables. Iceberg tables helped us in retrieve the data extremely fast, like within 5 minutes, not 5 minutes, like 2-3 minutes, we are getting the entire tables data, and it is efficient due to its partition pruning, metadata indexing, and it is extremely optimal. So if any guys, if you want to create this type of data mart, Iceberg is one of the good options, and we got it from our learning. So now, I will go to the machine learning model itself. Before deep diving into it, I want to discuss about what is a recommendation engine. So if anybody does not know about it, so suppose there are two users, user 1 and user 2. So both the user 1 has a preference of bread, butter and eggs, vis-a-vis the user 2 has a preference of bread, butter and jam. We will put these two into the algorithm. The algorithm will see the purchase behavior and will match it. So since these two customers are mostly similar to each other, as they both are buying bread and butter, it will recommend jam for user 1, which he has not bought. On the other side, it will recommend eggs for user 2, which he has not bought, but the other user have bought, along with bread and butter, where they have their natural preferences. There are two more terms which we should know while discussing about recommendation engines. The first one is the exploitation, and the second one is the exploration. Exploitation is the already recommending high affinity products, which is the, here in our case, bread and butter, which they are already buying to the user again, kind of a repeat purchase. And exploration means what we are seeing, the cross learning, that jam for user 1 and X for user 2, that the product that particular user is not buying, but the another similar user is buying, and we are cross recommending it. You guys might have seen this in YouTube. Specifically, when you surf through YouTube videos, you might have seen some other similar videos of some similar kind of, like, if you suppose, like for me, I like spiritual videos, so I got after watching 2-3 spiritual videos, I get another list of spiritual videos which I may not have seen earlier, but somebody else like me have seen. Okay, so before I go into the what has worked and what model architecture we have used, I want to see I want to tell what are the different experiments we have done. So the first, we tried to build one single model for all the customers across all the cities, but we have a huge database. Even that is why, even using a very big EC2 instances, we couldn't build the model with this with the full data. That is why we tried to choose a city-wise instance or a group of city-wise instance. So we trained the model on multiple cities using multiple instances. So that is what we have done. The second one is, we also, in the feature space, we wanted to create something called need segment. Need segment is like using the user interactions. We have created some clustering, and this clustering gave us clusters like pet shoppers, mango enthusiasts, non-veg vegetarians, and we used it in the metadata. But the issue is that it didn't give us good performance or any incremental benefit, so we dropped this experiment. The third is, I already mentioned that we have used ATB or add to cart or add to basket along with purchases in the model, but we also tried out views, the number of impressions and the clicks. But in our database, that data is little noisy. That's why it induced noise in the model, and again the performance hampered, so we dropped it. And finally, everybody is trying LLM. There is a huge craze or trend on LLM, so why should not we try? So we tried some LLM, some basic prompt engineering, RAG based data to create the recommendation engine model, but it failed because the latency was extremely high, and it also has a black box nature, because we don't have much debuggability into the model algorithm. So that is why the failure is simply the opportunity to begin again, and this time more intelligently, and let's discuss that, how intelligently we solve the problem. So the final model architecture that we have used here is light FM model architecture. So for the light FM, already I have mentioned about the metadata, user metadata, the interaction scores, and item metadata. We have transformed it into matrices, which are arrays, which are nothing but one-dimensional or two-dimensional representation of numbers. These features we have plugged into the model algorithm, which breaks this entire feature space into two embedding matrices, such that if we cross multiply these matrices, which are the user embedding matrix and the item embedding matrix, we will get the reconstructed form of the original interaction matrices. So first we calculate this user embedding and the item embedding matrix, and then we again do this score, which is like UI into VT, which you can see this equation, which is nothing but the cross multiplication of these two matrices, and it will again give back the reconstructed form. But in this reconstructed form, it is a little different. Here we will not only get the values for which the customer has interacted, but we will get the values for all the products where the customer has not interacted as well. So this score we will use at an affinity score. We rank it from higher to lower, and then we will finally give the final recommendations. In order to find out the values of these matrices, we have used the algorithm called stochastic gradient descent algorithm, which learns the values of these matrices using an iterative process, which minimizes the reconstruction error. So the error of the reconstructed matrix, the value of the reconstructed matrix minus the value of the interaction matrix. So we try to minimize this error. There are some loss functions like BPR, warp. If anybody wants to know, you can connect with me offline, and I am happy to discuss about that. So in order to, so the key advantage of this particular framework is that using this item metadata and user metadata, it strikes a beautiful balance between the exploration and the exploitation part. So item metadata and the user metadata helps in the exploitation part, and as well as it also helps in the cold start issues. Also, and the magnitude of the interaction helps in the sorry, I just went a little wrong. Like, so the metadata of information helps in the exploration part, where if it can map it with the similar kind of user using the metadata, and the value of the interaction matrices helps in the exploitation part. So if a person is already buying bread too much, it will automatically learn and it will recommend bread again to that person. So, and as a defect or as a key limitation, what we can say, it is a little expensive process, and we cannot create real-time systems out of it. We have to use batching. We have to train the model, run the inference once a month, and then use it recursively. So in order to gauge the performance of the model, we have used precision at 10, which is the percentage of relevance. Like if I select my top 10 products coming from the model recommendation as scores, how many of them the customer has actually interacted with. The other one is the ranking relevance, which is called NDCG, which is one of the most important metric, which gives us the measure of ranking quality. Like it's a rank ordered metric. So whether the model's recommendations rank ordering is exactly similar to the actual rank ordering of the product with which the customer has interacted. The reason we have used 10, because we have seen from our experience that people don't scroll more than 10 products or 10 assets in the home page. That is why we have used 10. Now I have given the benchmark numbers for precision and NDCG. You can see the numbers might sound lower because if there is any classical ML person, like why 88, 89% it is usually, and why I'm showing 5%. But since it's a recommendation or a ranking problem, and we have a huge feature set that I told you, there are lots of categories, lots of brands. That is why these numbers, even though the benchmark is lower, this lower benchmark is still good. And we have not used recall because recall is more of a coverage metric. We want more relevance. That is why we have not gone with recall metric. Again, I will discuss about the criticality, because though precision and recall is there, precision, recall, and NDCG is there. NDCG is a more important metric because it again measures the ranking relevance. So if there is a product which is highly relevant for a customer, and if we are ranking it lower by design of NDCG, it will penalize that metric extremely hard. So that is why we will immediately get to know that if there is a slight issues in the ranking. So that is why we have used NDCG and given more weightage to NDCG. So as like in the slide it is given that in a world of noise, ranking quality is the only signal that truly matters for the user. Now all of you guys might be eagering to see the performance results, but definitely abhi bhi picture abhi baki hai. So the movie has not ended. So I have already discussed about some constraints in the first slides. So let us discuss again about how we have overcome each of those constraints. So those constraints, to remind you again, first one is system latency, massive scale, minimal spark or EMR, and the last one is multi-domain usage. So let's discuss that how we have overcome each of these constraints. So for the system latency, after getting all the scores from the model, we have pushed it into an aerospike cache. On top of aerospike cache, we have built a high concurrent API service, a microservice, which which is used by the search backend service and the homepage backend service for the calls. So that is why we, in terms of the latency, we are not at the latency is not being compromised, I can tell. For the massive scale, already I mentioned that we have used parallel EC2 instances for to train the model at different city level. So that already reduced, helped in to reduce the, to handle the scale. But another thing, this is another learning that we want to share, that while, because LightFM is a typical ML model, we have not used the predict function of that model, because predict function takes a lot of time to do the scoring on this big data set. Actually, it was showing 2 days. So that is why what we have used is so we got the, from the model object, we got the embedding matrices, the user embedding and the item embedding matrices, and we have cross multiplied those matrices to get the reconstructed form, and we have used numpy array, basic numpy array. Numpy array is very fast because of broadcasting, and we have been able to do the entire scoring within minutes. And multi-domain I have already discussed. We have used 2 different frameworks, 2 models, one for brand, one for category, and 2 different databases. And for search, we are combining the brand and category scores with a weighted combination, which we have trained using a grid search on NDCG. And for category, we are using the category scores as it is. So as a key takeaway, we can say that through architectural innovation, we have transformed systematic bottlenecks into a high performance competitive advantages. Now, this is one of the best slides or most important slides throughout the presentation. So this is a new engine that we have built to avoid Spark and EMR. So I want to discuss on this. So this, for building this engine, we have used Polar's library, okay, which is built on Rust and which is 10 times faster than the Pandas normal data manipulation libraries. Now, for scoring the model, we have, based on all the users, we have broken the users into different chunks. For each of the chunks, we are passing it, so we have, for each of the chunks, we are converting the data into a numpy array. We are passing it whatever exactly the mechanism that I told in the previous slide, and we, using broadcasting and matrix multiplication using numpy array, we get the scoring. This scoring we are storing into ZAR, is a format in Python, which we are storing it into ZAR. Then on ZAR, we are again reading this model, reading this this architecture, and they are transferring it to Parquet format using Polars. So, and each of these chunks we are passing using multi-threading with a parallel 2D tiling of 5K into 5K. Now this question might obviously arise that why we are using this ZAR intermediate form? Because we are using a parallel processing and we are multi-threading, we are using, and we are passing huge amount of data concurrently. We using ZAR to Parquet helps us to avoid a lot of input-output bottlenecks compared to directly converting from a numpy array to the Parquet format. So that is why we use this, particularly this 2-stage format. And the other thing is, as a result, we have been able to write 2.5 TB of data with a 24x system in 1.5 hours. In terms of cost, I will translate that if you have used a Spark instance, even with a smaller Spark instance, this would have taken 3 to 6 hours and it would have costed around $30 to $60, and we have been able to achieve this with $12 only. So mostly at a half a cost, we have been able to do the scoring. So anybody wants to use this, we call it a fast dataset writer, our own proprietary product we have developed. So anybody wants any advice, so I can give, and you guys can use it for your work. So finally, the wait is over, and let's see the climax. As far as the performances are concerned, for the brand category and brand model, we have got a precision at K at 7% and brand at 10%. NDCG at 10 is at more than 23%, and in overall NDCG is 83%. When we have deployed this for 2 cities, Bangalore and Gurgaon, and we have deployed it for 50% of the customer bases, and we have got around 5% increase in conversion. So it got from 48% ATB conversion to 53% conversion roughly. We have deployed it in Q4 of 2025, and till now we are it's in the pilot phase, and we can see a 5% increase in the performance with respect to the control. Control is the population where this personalization model is not there. And the cost, this is the most important thing. In a monthly cost, we are doing one training and 2 inference pipelines we are running, and we are having a monthly cost of only $200. So a recommendation engine at this scale, we have been able to deliver with only $200, and this is the ROI number. So we have got a very high precision and cost effective model, which is driving around 5% conversions with a minimal operational overhead. So we have not stopped here. We are evolving this product. So first is that we are creating a feedback loop. So it's a dynamic feedback loop. So we have implemented the model, and we are creating mechanisms on top of the model, so that if a person is not interacting even after showing a product to a particular user, we will again put it in the next iteration training. So then we want to use more real-time inference models like SLM, VLM, and Cornac. Finally, we are also created a model which is when to buy model, like when after how many days a particular customer wants to buy a particular product, and we will try to integrate this with our recommendation engine scores. Finally, we are doing an entire search revamp and we are coming up with new LTR models, learning to rank models, which is a non-linear models, which will help us to incorporate the feedbacks much better. And so I will go to the final one, which is the key takeaway. So we have got a top tier NDCG and we are driving 5% more conversions with only $200 cost. We have designed a Spark-free dataset writer, which is writing the 2.5 TB of data in 1.5 hours. And finally, we want to implement in future feedback loops and new real-time models, which will help us to scale much better. If anybody, so I will end my session here. So if anybody wants more information, this is the place for you guys to contact me, and definitely I will suggest, as I move out of the dais, please go into the BigBasket app and see if you are part of this pilot or not. Thanks. Thank you. Sure.
Thank you, Subhodeep. That was a very inspiring talk. Now we have a chance and some time to ask a few questions, if there are any for Subhodeep.
Yeah, so I see you have used NDCG and precision. How do you create your data, like gold standard data? Do you have already existing data? Do you use users' data?
So no, we had a very unstructured form of data, because ATPs was in one place, your purchase was in another place. So first we created different layers. So the first layer is a bronze layer. So bronze layer means where you have your normal unstructured data. Then we created some intermediate tables, because this much of data you cannot process at one go. So we created intermediate data where we merged, suppose ATB and the clicks and views and all these things. And then we created aggregations on top of it, which is your gold standard data. And we finally ingested gold standard data. And some of the feature engineering we have done using polars directly in Python.
So the logic, what is the logic behind it? Like you show something and the user bought something like that goes into final gold standard.
Correct. So we use the add to basket, right? Add to basket means how many times he has added to cart, and purchases. So we have given a 1:10 weights, because purchase means you have an intent. Add to basket means window shopping you can also do. You have a choice. So that's why we have given a 1:10, and this 1:10 we have come up with after different experimentations.
Thank you.
Thank you, guys.